Hello everyone, this is Dr. Young, and in this video, this very short video, I'm just going to describe to you what it means to be an inhibitor or an antioxidant in terms of radical reaction. So the term is just referring to, right, antioxidants and inhibitors, it just refer to any molecule or substance that really slows or prevents these radical reactions from occurring, right? So in all of these previous videos, we've been talking about what radical reactions are, but antioxidants or radical inhibitors, they just stop that propagation step, right? Those propagation steps in a radical reaction. So I have two examples drawn here. This first one here, this is BHT, which is butylated hydroxytoluene, but I'll just put BHT for short. This is a food additive, oftentimes, so food additive. And this is synthetic. All right, this is made by folks in a lab, BHT, added to your Cheerios or something like that to prevent oxidation from occurring, to prevent radicals, right, oxygen, the oxygen radical, from messing up your food, making it spoil faster, making it go rancid faster. Since BHT is synthetic, usually we refer to that as an inhibitor. That it inhibits those oxidation radicals, those radical reactions. Over here on the right, I have sort of a simplified version of vitamin E. Which I'm sure you're all familiar with is one of the major vitamins, and it is naturally occurring. Which means most people are going to refer to vitamin E as an antioxidant. Really, these terms should technically be interchangeable, but typically people use the word antioxidant for naturally occurring things, molecules, inhibitors, radical inhibitors for synthetic things. The way these function, though, is going to be basically identical. And I'll just briefly show you how these two work. The idea is that both of these here have a similar functional group, which is an alcohol on an aromatic ring that makes it a phenol. And I'm going to use just some sort of generic radical here, right? Actually, let me give you a specific one. Let's not go generic. Let's just say it's a methyl radical, just to give you an example. Right, and like we were saying before in previous videos, right, these alkyl radicals are unstable and therefore reactive. Right, they're going to go try to find to abstract some sort of atom from something so they can become more stable, go downhill, become lower in energy. Now, as far as the reaction goes here, what we're going to see is that with molecules like BHT, your radical, whatever your radical is, whether it's oxygen or an alkyl radical or whatever, the idea is that this alkyl radical is going to abstract a hydrogen, which is going to leave me a radical on that oxygen. And I'll just draw that down here, what that looks like. So I'll redraw that whole molecule, that BHT molecule, the methyl, the two T-butyl groups, and then I have an oxygen with a radical and its two other electrons, right? So now I have this new radical, and then my CH3 picked up a new H and became a CH4. So I've just moved one radical to a different radical. But what's super important about these inhibitors and these antioxidants is now I've made a much more stable, much less reactive radical species, right? And the reason why this BHT radical that I just drew is much more stable is because it is resonance stabilized, right? I can start moving these electrons around to start showing how I have all kinds of delocalization for this molecule. So I'll draw my T-butyl groups on here. Now there's a double bond O, and I have a radical right here. I didn't touch that alkene or that alkene. I can keep on going, have this radical combined with one of these electrons, leaving a radical at that spot, which would give me this molecule. So I have a radical down there. And then there'd be one more, but I'm running out of room, so I'm just not going to draw it, if that's okay with you. But it would basically end up putting the radical now at this spot, because you'd have that electron combine with this electrons from that alkene, and then you'd have a radical there. But so the idea is that you took a very unstable radical, right, this methyl radical up here, And now it's a much more stable, much less reactive radical. So I'll say this whole thing right here, right? This whole sucker is very stable. It's a very stable radical. And therefore much less reactive. It sort of quenches that radical, makes that radical not reactive anymore and no longer able to do all those propagation steps. So it kills the radical reaction. It stops it. If you were to add a whole bunch of something like BHT to like a radical chlorination or bromination, the reaction stops. And in fact, that's a tool that chemists use to see like, you're doing a new reaction, no one knows anything about it, you're not sure about the mechanism. One easy thing to do is to throw in a radical inhibitor like BHT, like other things, other phenols, and see if it stops the reaction. If it stops the reaction, your reaction is probably a radical reaction. And I'm not going to draw it for your vitamin E, but vitamin E does the exact same thing, right? So what we're looking for a large class of antioxidants and inhibitors, and this is not the only antioxidant and inhibitors out there, but what we're looking for is this phenol group, right? An OH on a benzene ring, right? So this is a phenol, and it's just made of hydroxyl on a benzene. You may already know that functional group. If not, now you do. And so you'll notice that vitamin E has that, a hydroxyl on a benzene ring, which is why vitamin E is an antioxidant. And I'll note that a lot of your other vitamins are not antioxidants, right? Like a lot of the B vitamins are not very good antioxidants. Vitamin D is not a great antioxidant. Vitamin E is. Vitamin C is great. You may have heard about vitamin C for like when you have a cold or something like that, or they'll add vitamin C to foods to make them so that they don't go rancid, they don't get oxidized too quickly. Vitamin C is a really good antioxidant, but you'll see, if you look up the structure for vitamin C, you'll see OHs that when you make them radicals, they are resonance stabilized. So vitamin C is pretty good too. I mentioned vitamin E here because you may have heard about vitamin E causing issues with vaping. Vitamin E was being put in a lot of vaping formulas, juices, formulas, especially ones that had cannabis extracts. And the reason why vitamin E was put in those was to prevent the oxidations of those cannabinoids. And so there's a lot of vitamin E that people were inhaling, and it looks like that was not exactly the safest thing. It was causing some respiratory issues. But vitamin E is also put in foods, again, to help preserve them, and again, to help them not oxidize so quickly and not go rancid so quickly. To just give you some other examples, I know, again, that we've heard a lot about antioxidants just in terms of foods and stuff like that. Here's a whole bunch that I stole from a paper. We have flavonols, right? Let me give my little cursor here, right? So flavonols, flavones, so like quercetin, you may have heard of quercetin. We have some flavones, we have some flavonols, anthocyanins. These are like the things that are really, really colorful. So like, think like blackberries and blueberries. Flavonones, isoflavones. So these would be things like in soy. So when you hear about these antioxidants in foods, hopefully you can look at these and be like, oh wait, yeah, of course these would be antioxidants, because if you look at these, right, you see a whole bunch of alcohols on aromatic rings, right? Alcohols on aromatic rings, alcohols on aromatic rings. These are all have lots of phenols on them, right? So sometimes they're called polyphenols. You may hear the term polyphenols for another term for antioxidants that you'd find in foods. And again, they behave as antioxidants because they're able to find that radical, or when that radical finds them, rather, it makes a much more stable, resonance stabilized, delocalized radical that is not able to do propagation steps anymore, and so you prevent that radical damage. And it's antioxidant because, if you remember from earlier videos, our main oxidant that we're concerned about as living creatures, hopefully this is your main concern, is just good old O2, that diradical oxygen. That's the one that we're worried about, in theory worried about. We may not be, it turns out, but current nutritional theory is very concerned about oxidative damage and free radicals, and so you eat antioxidants to chew up those free radicals. That's all I really want you to know about inhibitors and antioxidants. They just basically work by making much more stable radicals, and so they stop those propagation steps. And you should be able to identify them as molecules because for us, at least in this class, they're going to be phenol-based. They're going to be phenolic in nature. So this is the end of our radical stuff. Happy studying. Good luck. Let me know if you have questions.